Hi, this is Mrs. LaBarbara. This is AP Physics Chapter 8, Momentum, Impulse, and Collisions, Video 3. Today's topic is momentum conservation and collisions. The objectives are understand the difference between elastic and inelastic collisions, be able to apply energy conservation and the momentum conservation principles to solve problems. Elastic and inelastic collisions. In physics, we broaden the meaning, the term collision, to include any strong interaction between bodies that lasts a relatively short time. If the forces between the bodies are much larger than external forces, as is in the case in most collisions, we can neglect the external force and treat the bodies as an isolated system. The momentum is conserved during a collision. If the forces between the bodies are conservative during a collision, such as in this case, the force between the two objects are the force from springs, then the total kinetic energy of the system is the same after the collision as before. That means kinetic energy is conserved. Such a collision is called the elastic collision. However, if that is not a case, such as in most cases of collision, total kinetic energy is not conserved. That is different than before, different from before and after. In that case, the collision is called an inelastic collision. Another type of collision is a special case of inelastic collision that's called completely inelastic collision. In such a case, the two stick together. So the object 1, the velocity of object 1 and 2 are the same, equals to V2, they stick together. In a completely inelastic collision, the momentum is conserved, but kinetic energy is lost. Where did it go? Kinetic energy after collision, most likely it went into the heat, other types of energy. Usually it's less. It is less. Okay, caution. An inelastic collision doesn't have to be completely inelastic. So completely inelastic is just a special case of inelastic. Again, only in elastic collisions, the total kinetic energy before equals to the total kinetic energy after the collision. Special case of inelastic collision. So this is a general case of inelastic collision. The two stick together. Special case is this. A body with mass ma and initial x component velocity va1x, 1 means before, collide inelastically with a body of mass mb that is initially at rest. That's a special case. One is moving, the other one is rest. And after they collide, they stick together. The velocity of both bodies after the collision, v2x, equals to, substitute everything in, this term becomes 0 because mb is at rest. v2x is ma divided by ma plus mb times the velocity of a before collision. The kinetic energy before the collision is just kinetic energy of ma, which is 1/2 ma va 1x squared. Again, 1 represents before collision. Kinetic energy after the collision, you add the two together times velocity after. Substitute velocity after from this expression, this is what you have. You can simplify it. The point is, here is the proportion for kinetic energy after relative to kinetic energy before. So as you can see, kinetic energy after is less than kinetic energy before, is ma divided by ma plus mb. So it depends on that mass ratio. So this is kinetic energy relationship of completely inelastic collision for object B initially at rest. Again, I do not recommend you to remember this equation, but you need to kind of know how it is derived to understand its derivation. Let's take a look at this example. Suppose we repeat a collision described in example 8.5, but this time equip the glider so that they stick together instead of bouncing apart after they collide. Find a common final velocity V2x and compare the initial and final kinetic energy. For those of you who doesn't remember example 8.5, that's two objects. Now, instead of they bouncing off each other, the two objects collide, stick with each other. Here is MAVA before, MBVB before, what is velocity after? So this is completely inelastic collision. Simply, this is the equation for completely inelastic collision. We substitute it in, and you can solve V2x equals to 0.5. So the two objects move at a slower speed. Now let's check the energy. Kinetic energy before the collision is kinetic energy of A plus kinetic energy of B, which is 1.6. Kinetic energy after the collision, you use the 2 prime means after. Similarly, like what we did in regions, it's 1/2 MA plus MB times V2x squared. You have 0.1 joules. So before is 1.6, after is only 0.1. So as you can see, the final kinetic energy is much smaller than the original kinetic energy. That is because kinetic energy is converted into heat during collision. So the the blocks will get hotter. If there is a spring between the glider, however, the kinetic energy will be stored as the potential energy of the spring. Then eventually they separate. They will have the same kinetic energy as before. The total should be the same. The total energy, however, and the total momentum is conserved in all collisions. Total energy is the total. Remember the mechanical energy plus internal energy before should be equals to after. But only kinetic energy is conserved during elastic collision. Let's take a look at another example. This is ballistic pendulum. So here's a bullet, mass MB is fired into a block of wood with mass MW suspended like a pendulum, and it makes a completely inelastic collision. That means the bullet is going to be embedded into the block of wood. After the impact of the bullet, the block swings up to a maximum height, y. Given the value of y, mass of the bullet and mass of the wood, what is the initial speed v1 of the bullet? So diagram a situation. Here's a bullet hitting the block. This is before collision. This is after the collision. The bullet is embedded in the wood and the wood is going to swing. So here is y. And here is the speed v2. So the question is, what is the initial speed v1? Using conservation of a momentum, we know m bullet times v1 equals to the two added together times v2. But in this case, we don't know what v2 is. But from the conservation of energy, we know energy is conserved. Okay, by the way, from v1, from this equation, we can find what v1 is. Next one is from conservation of energy. Total energy is conserved. In this case, it's just from kinetic into potential. So we can figure out what is V2 equals to. Once we have V2, we can use the top equation to figure out V1. So that's how you solve. You use conservation of momentum and conservation of energy principles to solve it. So let's do an example. Suppose the bullet is 5 grams and wood is 2 kilograms and y is 3 centimeters. What would it be V1 equals to? So from here, we can solve for V2, plug everything in, and here's V1 would be 307 meters per second. Okay, so we can figure out what is the total kinetic energy before. That's 236 joules. Total kinetic energy after only 0.589 joules. So where did the kinetic energy go? So in most cases, nearly all the kinetic energy disappears as the wood splinters. The bullet and the block becomes hotter. So basically, all that kinetic energy is transferred into internal energy. Another example, an automobile collision. So 1,000 compact car is traveling north at 50 meters per second when it collides with 2,000 kilogram truck traveling east at 10 meters per second. All occupants are wearing seatbelt and there are no injuries. But the two vehicles are thoroughly tangled and moves away from the impact point as one mass. The insurance adjuster has asked you to find velocity of the wreckage just after impact. What do you tell her? So this is a situation of collision. Draw a picture. Here is the car before, right? Here is the car after the two colliding. The momentum is going that way. So this is a case of inelastic collision and a completely inelastic collision. P before equals to P after. That's a constant. What is P? Well, P equals px squared plus py squared because you have two dimensions now. And P, remember, is a vector quantity, so it has a direction. When you ask a direction, you have to give the angle. We use inverse tan to find the angle. So, but what is px? Well, px is all the x component add together, 2,000 times 10 plus 1,000 times 0, because 1,000 compact car has no horizontal velocity. So px is 20,000, similarly py is 15,000. When you plug in this equation, you will have p equals to 2.5 times 10 to the 4 kilograms times the meter per second, and the angle, this is special case of 345 triangle, so the angle is 36.9 degrees over here relative to the x direction. So this one is asking you, what is the velocity? Velocity is momentum divided by mass. And here's total momentum. We'll have to use total mass. So the velocity is 8.3 meters per second, and the angle is the same as the momentum. Momentum and velocity always have the same direction. Okay, test your understanding. So for each situation, state whether the collision is elastic or inelastic. If it is inelastic, state whether it is completely inelastic. First, you drop a ball from your hand, it collides with the floor and bounces back up so that it just reaches your hand. In this case, so you know potential energy is changing to kinetic. When it bounces, it's kinetic, then becomes potential again. So in this case, kinetic energy is conserved. So the collision is elastic. Next one, you drop a different ball from your hand and let it collide with the ground. And this ball bounces back up only half the height from where it was dropped. So you know kinetic energy, potential energy halved, so kinetic energy must halve too. So it's inelastic because kinetic energy is not conserved. You lost kinetic energy. 3, you drop the ball of clay from your hand. When it collides with the ground, it stops. This is a case of a completely inelastic collision because the objects in this case is the clay and earth stick together. That's it for today. Thanks for watching. See you next time.